Hello, my name is Jesse Vela. I'm a computer science student at University of Houston, and my ORU project is applying material informatics to high entropy alloys. So when you discuss data science and material informatics, you must mention the Materials Genome Initiative. The motivation behind much of the data science and materials informatics being conducted today is the Materials Genome Initiative. The goal of the MGI is to accelerate the discovery, development, and deployment of new materials. The MGI was created in 2011 in a time when artificial intelligence was advanced, but not as advanced as it is in 2023. With the rapid development of machine learning, big data, and big compute power, MGI initiatives only become more important. So there are 5 aspects of MGI, and that's conducting a lot of experiments, properly storing data and knowledge, conducting advanced simulation, conducting material informatics and advanced statistical analysis, and materials design. So we've been doing material informatics on high entropy alloys. High entropy alloys seem to be very popular at the moment from an outside perspective, but the large number of potential high entropy alloys make it a difficult class of materials to study because the metals can be so varied. Because high entropy alloys can vary so much in composition, there is a lot of opportunity to design HEAs with tailored properties. The largest publicly available dataset of HEAs was compiled by Borg et al., and here's a brief overview of the database. There are 745 single-phase entries, 669 multi-phase entries, and of those 745 single-phase, 468 of those are body-centered cubic, and 265 are front-centered cubic. In my research, I've mainly been focusing on single-phase and BCC alloys. In terms of mechanical properties, there are 619 ductility experiments in the database, 1067 yield strength tests in the database, and 530 hardness tests in the database. Here's the intersection of these mechanical tests. The Venn diagram shows the number of alloys that have an experiment with any combination of hardness, yield strength, or elongation records. And here we see that in the experiments conducted to form the dataset, yield strength is collected with elongation for most alloys. Hardness is collected with a lot of alloys alongside yield strength, but it's also collected alone a substantial amount of the time. This is an elemental co-occurrence network. It describes how frequently elements appear together in alloys in the database. In terms of the elements that make up the composition of the HEAs in the database, we see that cheaper and more readily available elements are often utilized, with harder to obtain elements such as rhenium being used very sparingly in the dataset. Given the data in the Borg dataset, the goal of this project is to create a multi-information source model that can be used to better optimize for yield strength. A popular surrogate model for Bayesian optimization is the Gaussian process regressor. This is because GPs natively provide a prediction and plus or minus uncertainty bound on that prediction. And in this work, we will use hierarchical Gaussian processes in order to use hardness as a cheap proxy experiment for yield strength. In this toy example, we are adding points to a cheap proxy experiment and continuously sampling functions from the cheap proxy to plug into our expensive truth experiment. In this case, it would be hardness into yield strength. The expensive truth function only has a set number of experiments, but we are allowing what we're calling the cheap proxy to gather more data. And we see that as we add data points to the cheap experiment, the model becomes more accurate, making the expensive experiment more accurate, even though we are not increasing the number of data points that the expensive experiment is seeing. The purple line here is one of the many functions generated by the proxy GP. The truth GP here is trained with the red points evaluated on the purple function as an extra input, and this is repeated for many samples, and the truth GP is recorded for each. This propagates the uncertainty of the cheap GP into the expensive GP. Here we see one of the benefits of propagating that uncertainty and utilizing chain GPs. We see that adding experiments to the proxy experiment in the same input space reduces the uncertainty of values in the truth GP. We see that in regions with queries in both the truth and proxy, uncertainty is substantially lower than in regions with only truth queries. Here are the results of the hardness to yield strength hierarchical GP without uncertainty being propagated through the usage of sampling functions, and it's cross-validated with 3 folds. We see a Spearman correlation coefficient of 0.82, an MAE of 216, root mean squared error of 286, and R2 of 0.62, or R squared of 0.64. In terms of data preparation, we've prevented temperature series experiments from being split across train and test, and we have filtered the data set for BCC alloys. And here are the results of the same model, but uncertainty has been propagated through the usage of sampling functions and training many yield strength GPs. We use the same 3 folds and sample the functions of the hardness GP 5 times, generating 5 yield strength GPs with a 3-fold split and averaging their outputs. And we see that all the metrics recorded have improved, indicating that propagating the uncertainty is a benefit and increases the accuracy of the model. For future work, we intend to further extend the hierarchical GP to predict fracture strain, and we'll also continue investigating other multi-information source GP techniques, such as multitask GPs. And the overarching goal of the project is to use the best performing data-enabled model to design strong yet ductile alloys. And here are my references. Thank you.